Hello, grade 11s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Oabutiwa Sos Ugwabela Wemet. And without any further ado, let's look at these questions that we have here. Okay, so we have question 4, still on Newton's second law. It says two blocks of masses 1.5 kg and 3.2 kg are connected by a light inextensible string. A 24 Newton force is applied on a system of blocks to move them up an inclined surface, which is 25 degrees to the horizontal at a constant velocity. Note that constant velocity, which immediately tells us that our acceleration is 0 meters per second square. Right, as shown on the diagram below, the 1.5 kg box experiences a constant frictional force of 2 newtons as it moves up the incline. Right, so note that we are only told about the constant frictional force of the 1.5 kg and nothing is said about the 3.2 kg. Right, so do not assume that the friction in the 1.5 kg is the same as the friction in the 3.2 kg. They did not mention that. Then 4.1 says, state Newton's second law of motion in weights. So we already know, we say that when a net force is applied to an object of mass, the object will accelerate in the direction of the net force, where acceleration is directly proportional to the net force and inversely proportional to the mass of the object. So that's how you are supposed to define that for a total of 2 marks, right? Then 4.2 says draw a label-free body diagram of all forces acting on the 1.5 kg block, right? So the best way to just draw this one is to just start with the incline, but then you always have to remember that after you are done, you have to erase that incline. So it's just to make it easier for you to draw these forces, because now they're on an incline, they need to be perpendicular. So your normal force needs to be perpendicular to the inclined surface. So it's best when you start drawing that incline there, so that it kind of, you kind of see when it becomes a perpendicular there. So let me just erase here. Then let me try to just draw it straight. Then we know that always in line we will have our FG perpendicular in the same line with our normal force, but then facing the opposite direction downward. And then here we know that the FG parallel is always sliding down the incline. So where the incline is sliding down, that's where you'll find your FG parallel. And then up here, up the incline, we have tension. As we can see, the rope here is being connected this side in reference to the 1.5 kg. And then what else do we have? We have the frictional force. So since the blocks are moving, we will say this is the kinetic frictional force. And then how many forces have we got? Remember, these are components of weight, so they mark them as 1. And then that means you have the mark for this one, you have the mark for that, the mark for here, and the mark for that. So that's 4 marks, 4 forces. Right. Then we are done with that. Easy peasy. You could have just got your 4 marks like that. Then in 4.3, they say calculate the tension in the string connecting the blocks, right? Now note, we are told that this is constant velocity. So this is not a simultaneous question. Why? Because in a way we are given the acceleration. The acceleration is 0 meters per second square. Remember, it only becomes a simultaneous type question if we don't have the magnitude of the acceleration and also we don't have the magnitude of the tension. But here, because we do have the magnitude, meant to say, of the acceleration, then that means we cannot be applying our simultaneous equations here. We need to work using the 1.5 kg block as drawn here. So what are we going to say? Using our Newton's second law formula, which is F net is equals to ma, we do understand that if this system of blocks is being pulled upward, then this makes our upward being our positive direction, and then down the slope here becomes our negative direction. So up the slope is positive and down the slope is negative. So that means we need to indicate this as tension minus the FG parallel minus the Fk, right? So what do we want? We want the tension, right? And then this is equals to mass times acceleration. Now we can break this one here. Remember, the Fg parallel breaks down to mg sine theta. And then let's just go ahead and substitute that. We have T, and then our Fg parallel will be our mass, which is 1.5. Our gravitational acceleration is 9.8. And then we have sine 20 degrees. Remember, the theta now is the angle of the incline, right? And then remember, we are told that the constant frictional force in the 1.5 kg block is 2 Newton. So we have minus 2 here. Then our mass is still 1.5. But then remember, the acceleration is 0 as a result of this keyword here, constant velocity. Then we have 0 there. Now, having to punch all this in our calculator, it will give us negative 7.03 rounded off to 2 decimal places, then equal to 0. So obviously our tension is 7.03 Newton if we transpose it. And then that's how you could have found the magnitude of the tension there. And then now 4.3.2 for 6 marks, it's saying calculate the coefficient of kinetic friction force between the 3.2 kg block and the surface, right? Now, we are on the 3.2 kg, so that means the first thing that we need to do here is to show all the forces acting on the 3.2 kg. So we can do that by just drawing the free body diagram for the 3.2 kg. So that means we'll have the normal force here. We'll have okay. So let's draw it here. We have the normal force, and then we have the Fg perpendicular. Then down the slope, we know that should be our Fg parallel. But then also down the slope, in reference to the 3.2 kg, we can see that the tension is now down the slope. So we have tension here. But then we also have another force that is acting down the slope. That's the kinetic frictional force, because remember the block is moving up the incline, so that means the kinetic frictional force needs to be down the incline. Then the only force acting up the incline is the force applied, which is causing the whole system of block to move upward. Right. Okay, so now that means in calculating that, we need the coefficient of kinetic friction. So the first thing that we try to figure out here is the normal force, because we know at the end of the day, we must use the formula Fk is equals to mu k times n. Or if we want the mu k, as they say there, we must use the formula Fk over the normal force, right? So, but then the basis is that we need to first find the normal force here. So how can we find the normal force? Remember, on an incline, every time we are on an incline surface, then we have to always remember that our normal force is equals to the Fg perpendicular. So to calculate our normal force, let's just go ahead. We have normal force is mg cos theta, right? Then our mass is 3.2. And then we have 9.8, then cos 20 degrees, right? Now, punching this into your calculator, we get 29.47 newtons. So this is our normal force. But what is it that we need in order to calculate the coefficient of kinetic frictional force? We also need the frictional force itself. And then remember, we cannot assume that our frictional force is 2 newtons. Remember, this 2 newtons is only applicable for the 1.5 kg. But then the 3.2 kg also has its own kinetic frictional force, which we would need to calculate using our Newton's second law. So remember, this is moving up the slope. So this is our positive direction. And this here is our negative direction. Note what I told you, always with the negative direction, you will be able to spot the negative direction by looking at the position where Fk is, right? So Fk is always on the negative direction. Okay, then now we have F net is equals to MA, and they should be written as the positive forces minus all the negative forces. So we have Fg parallel minus tension minus Fk. So we are looking for that Fk and then equal to Ma. Remember, this is still moving at a constant velocity. It is also applicable to the 3.2 kg because it is the whole system that is moving at constant velocity. Then our force applied is 24 newtons. So let's substitute there. Our FG parallel, we still remember FG parallel breaks down as mg sine theta. So this is supposed to be 3.2 multiplied by 9.8 and then sine 20 degrees. Then the tension there, it's supposed to be the tension that we calculated previously, because remember, in a system, the acceleration is the same and also the tension is the same. So we want to substitute the value that we got here, which was 7.03 newtons. So the tension experienced by the 1.5 kg is the same tension experienced by the 3.2 kg. Then that's 7.03 minus Fk. Then here we have 3.2 multiplied by 0 because of constant velocity. Then if we punch all this into our calculator, we get 6.24 and then minus Fk is equals to 0. So that means our kinetic frictional force is 6.24 newtons if we get to transpose there. But then remember, we are not looking for the magnitude of the kinetic frictional force, but we are looking for the magnitude of the coefficient, right? So that means that this is where now we get to apply that formula. Mu k is equals to Fk over the normal force. And then our mu k is equals to Fk is 6.24, and then our normal force is 29.47. Now, punching this into your calculator, we have 0.21, which is our coefficient of kinetic friction force, right? And then remember, we have no SI unit here because we say this is a ratio of the normal force and the kinetic frictional force. So ratios do not have any SI unit. And that's it for the lesson, guys. Please press the thumbs up button if you've enjoyed the lesson and then you have found it helpful. And if you've been watching the videos and haven't subscribed yet, please hit that subscribe button. But most importantly, please share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.